couldn't speak French as fluently as you do, so I was speaking English. So let's start with the definition for Kakeya set. A Kakeya set in Rn is a compact subset containing a unit line segment in every direction. So the question is, how small can a Kakeya set be? Basikovich showed that I could have zero measure via this construction. You take an equilateral triangle and then cut it into many small pieces and then move them, the pieces closer to become like a tree-like structure, and this tree structure still contains all the line segments in here, and if you do some calculation you will see that this measure goes to zero as you decompose into finer and finer triangles. So the Kakeya set conjecture states that any Kakeya set in Rn has Hausdorff dimension and so for the lectures, for today at the beginning, I'm planning to go through some definitions and set up and also prove the two-dimensional case. So I should say that n equals to 2 was solved by Davis. And then n equals to 3, there has been many people who work on it, that our proof was largely influenced by their ideas and work. For Bochen, Wolf, Katz, Laba, Tao, and also the work of Larry Guth. And Katz, Zahl. And then the dimension n greater or equal than 4 is still open. So as we go through the argument, we'll emphasize which part is influenced by which paper. So today I'm planning to cover the two-dimensional case with this an argument due to Cordoba, and also maybe beginning so the plan is a 2D case, and then the proof is decomposed into the sticky Kakeya set and the general Kakeya set. So for today, we are going to go through 2D and some of the ideas in the sticky Kakeya sets. So for this part, we are going to talk about details for the arguments that are going to be used in the last part. And then we are going to sketch some of the ideas that are sort of within sticky Kakeya set, and that's not going to be used in the last part. And starting from maybe tomorrow, the second half of the lecture, we'll start talking about details of how to go from sticky to non-sticky in more details. And also, so together with Larry Guth and Josh Zahl, we are writing a more streamlined proof based on the outline that Larry put on arXiv. So I hope to put it on my website later today, so that when some of the details that I skip, I could point it to you, the reference there. Okay, so let's. So this is a conjecture about house of dimensions. And so the way we usually think about house of dimension is to discretize. So we pick a small scale. Let's say delta is a very small scale. And we said delta tube. So since Kakeya set contains many unit line segments, the delta neighborhood of a unit line segment is a delta tube. T has radius delta and length 1. So, and then what does this Kakeya set look like after thickening to scale delta? So we have this Kakeya assumption. So this means that a set, this blackboard T means a set of delta tubes. This T means one delta tube. So a set of delta tubes so a set T consists of one delta tube in every delta separated direction. What it means is that on the unit sphere, we take a delta net. So the distance between a point and its neighbor is roughly delta. And for each direction in this delta net, we take a delta tube. And for example, let's say for this direction, we take this delta tube, but we could move this delta, translate this delta tube for this direction. And for the other direction, we take another delta tube in this direction, and also we should feel free to translate it. So we want to state a discretized version that would imply the Kakeya set conjecture with house of dimension version. So to make this rigorous, we need to define the following. Let's say shading on a delta tube T. So a shading is, so this is YT, we will let YT to denote shading, is a union of delta balls. So the word shading is really just a subset of the tube, but we say shading because it's a union of delta balls, and delta is like the radius, the minimum side length. Okay. So that is the difference between shading and a subset. We define the density lambda y. So let's say we can also say that this says y, a shading y. So maybe I should say a shading y on a set of delta tubes. Just means that for each t we think YT as some map from this T to the subset. And so the shading Y on T has density lambda Y. So the definition is just we sum over the measure of YT is roughly lambda T times the volume of 1T times the cardinality. So we use this to denote cardinality and this to denote volume. So usually we care about, so in the in the lecture, we care about lambda t to, lambda y, the shading, to be greater than delta to the eta for some eta small, very small. For the more general problem, it's also interesting to study when this should be shading y. In general, it's also very interesting and much more difficult to study the case when shading is like much less than, let's say it's like delta to the 1/2, for example. It's much more difficult. But for the sake of proving the Kakeya set conjecture, it suffices to study the shading when it's like sufficiently large. And usually this eta goes to 0 very quickly. Okay. So the discretized Kakeya set conjecture says that the quantifiers throughout the lectures will always be like follows. For any epsilon greater than 0, for any eta sufficiently small depending on epsilon, the following holds for, again, delta sufficiently small. So let T be a set of delta tubes satisfying the Kakeya assumption and Y be a shading on the set of delta tubes with density greater or equal than delta to the eta. Then the union of tubes, I will explain this notation immediately, is greater or equal than delta to the epsilon. So this notation, let me just write it here. So U, T, Y just means the union of shading when T is in our collection. Okay. So this is the discretized Kakeya set conjecture, and using the definition of Hausdorff dimension and by pigeonholing, if one can show this discretized Kakeya set conjecture, one could show via a classical argument in geometric measure theory that any Kakeya set in Rn has Hausdorff dimension n. Okay. Yeah. So. Yeah, I just said what I said. So I want to save some time. One should think this 0 delta is much smaller than eta and much smaller than epsilon. And also, if you if it's totally fine to not care about shading and to ignore a lot of pigeonholing. So if you just want to have a sense of how the argument goes, you could pretend the shading is just the entire tube. A lot of the intuition still holds. It's just that if we want to have a rigorous argument to go from to prove this conjecture, you need to prove for like sufficiently dense shading rather than the entire thing. So I will try to explain the difficulty of the Kakeya set conjecture. So one thing is that for this Kakeya assumption, if a set of tubes satisfies the Kakeya assumption, then it implies that the number of tubes is roughly delta to the minus n minus 1. Because if we take a delta net on the unit sphere in Rn, then there are roughly delta to the minus n minus 1 many points and many directions, and in each direction we have one and only one delta tube. So this says that the number of delta tube is roughly delta to the minus n minus 1. This Kakeya assumption is difficult to induct. The reason is that if we have a set of delta tubes, let's say with one in every direction, it satisfies the Kakeya assumption. Then when we want to do induction of scales, we usually, let's say, intersect this with some small box or small fat tube. And then we get a bunch of tube segments. So there is no guarantee that those segments will satisfy the Kakeya set, Kakeya assumption. Even if we take let's say, we take a thick tube, let's say this one, then again there is no guarantee that the thin tube contained in this thick tube after the rescaling would satisfy the Kakeya assumption. So this is why this assumption is very difficult to use, and it's very difficult to induct. So this says, maybe I should also say that please feel free to stop and ask questions if you have any. So far, do you have any questions? Okay. So the next topic is what is a good assumption on the set of tubes. So we just said that this Kakeya assumption is difficult to induct. So we want to have some assumption that is more convenient to do induction of scales. And eventually we hope the following holds. So when we say a good assumption, we want to achieve something. Then what do we want to achieve? So that the union of those tubes has volume greater or equal than delta to the epsilon in the same sense. The minimum of number of tubes times volume of one tube and one. Let's say on the set of delta tubes contained in the unit ball, so that the reason is that the Kakeya set is a compact subset. We might as well assume that all the tubes are contained in the unit ball, so that we have the following volume lower bound for the union of shading. So that the correct statement is for any y, for any shading with density greater or equal than delta to the eta. Again, eta delta epsilon is there in the same sense as this conjecture. So what is a good assumption? The terms here means the following. This term, if we ignore this epsilon and eta, this first term just means that the set of tubes, they are essentially disjoint, because if they are disjoint, then the volume of their union should be like the number of tubes times the volume of one tube. And then the second term means that the set of tubes, if there are too many, the second term just means that they essentially fill out the unit ball. So this right-hand side is the best possible bound. Like it cannot be more than completely disjoint, and also it cannot be like more than full. Okay, so this is the question, and our goal is for this question is in some sense more difficult than the Kakeya set conjecture, because the goal is to give some very nice criteria such that we have the best possible union bound. So there is this enemy example. That is, if W is, let's say, A times B times 1 rectangular box, then usually when we write something like this, we mean A less or equal than B less or equal than 1. So we always write the smallest scale in the front, and assume that we also have A is greater or equal than delta, so that W contains at least one delta tube. And we take T to be all distinct delta tubes contained in W. So distinct means T1 and T2, they are distinct, just means that their intersection has volume less than half of one tube. We need the assumption to be distinct, because otherwise we can keep repeating the same tube at the same place. So it doesn't really make sense to talk about this volume bound. So that's why distinct is like sort of the minimum assumption. And so we take T to be this, I should say, all distinct means, let's take T to be a maximum set of distinct delta tubes contained in W. Then how many are they? So here, this is a box. So A, B, and 1. There are the number of T is W over T square. Roughly the volume of W over the volume of T squared. The reason is that the set of directions of tubes contained in this rectangular box is roughly the directions corresponding to roughly this A times B rectangle. And then each delta tube corresponds to a delta cap, a direction delta cap on this unit sphere. So how many directions are they? The number of directions is roughly AB over delta square, which is the volume of W over the volume of T. So we have this many distinct delta separated directions. And then for each direction, how many can we pack? Like we can pack parallel tubes, because so if they have distinct directions, they are by definition distinct. And also in the same direction, the disjoint parallel tubes are also distinct. So this gives us also the volume of W over the volume of T, many tubes per direction. So this gives us this number times this number, that is the square. And then for any shading, we might as well take the shading to be the entire tube. This union is less or equal than the volume of W, because everything is contained in W. And now if we want to compare this quantity here, we know that ideally we hope this guy to be large, but for this example, the left-hand side is W and the right-hand side is the number of tubes times T is like W over T times W. So this volume is smaller than the right-hand side by this factor. So this is usually is much bigger than 1 if the volume of W is much larger than the volume of T. And this is by how much with this example fails what we want to prove. So this is an easy enemy example. So what we proved, it can be summarized as in dimension 2 and 3, that's the argument that we are going to see for the lectures. This is the only enemy example, and in higher dimensions there will be other enemy examples. So based on this enemy example, we could define a different assumption than the Kakeya assumption. That is, so before doing that, let's define the density of T in W. So this density is quite natural. It's just the follows. So this is roughly the number of tubes contained in W times the volume of one tube divided by the volume of W. So T bracket W means so in fact, I think as it's so this is a natural assumption because in order for this to hold, from this enemy example, we can see that okay for this example, what is the density? It's precisely this volume of W divided by volume of T. And from this enemy example, we see that in order for that estimate to hold, we want the density to be bounded by 1. And so this is a natural definition. But later, for in some of the arguments, we need to consider more general object. So I'm going to just generalize this definition slightly. Okay. So maybe I should ask, is everything clear at this point? Okay. So this is just a slight generalization. Let's say let V be a set. It looks slightly abstract, but in reality, you should think V as so this blackboard V as a set of delta tubes, or a set of A times B times 1 rectangular boxes. And for these lectures, they are just essentially these two options. Either V is a set of delta tubes, or V is a set of Ws. So it's quite simple, but I'm just stating the definition in a more general way. Hopefully, this could be used in other setting, in Rn. And W is also a subset of Rn. Again, here this W is we should think as some sort of convex set or semi-algebraic set. But as you can see that this is so this is just a mild generalization of this density for arbitrary set of convex sets. We say that, again, I'm stating this is just hopefully this definition would be useful for higher dimensions, but in 3D we just really only care about delta tubes and those A times B times 1 boxes. Definition, we say that V satisfies Katz-Tau Wolff axioms with arrow C. So we write it as, so this just, we write this cat tau kt constant, cat tau constant of V is less or equal than C. And if the maximal density of blackboard V, a set of subsets, equals to the maximum of W, so since is less or equal than C. So here we take W to be a convex set. So usually it's Kastel-Wolff convex Wolff axioms. So that's the first definition. Because this definition is motivated by this enemy example. So as you can see that if V is a set of delta tubes, then we hope to say that if the maximal density of a set of delta tubes is bounded by some constant, then hopefully it satisfies the first bound. That's the goal. And there is also a slightly closely related but different definition. We say that V satisfies Frossman Wolff. Sorry, maybe I should put the convex here. Kastel convex Wolff. Frossman convex Wolff axioms in a set W with arrow C. So we write this as, there are a lot of names. I hope I can explain why we use this very long list of names. So we write it as Frossman constant in W less or equal than C. If for any convex set W prime in W, so W is also a convex set, the maximal density, so the density of V in W prime is less or equal than C times the density of V in W. So that is this definition. So now let's digest this definition a little. Let's see. Maybe I can erase this. Yeah, this is the main definition that we are going to work with throughout the lectures. So to digest it, let me first state the conclusion, so the theorem, and then we'll digest the notation further. So the theorem is when n equals to 2 is due to Cordoba. When n equals to 3 is by Josh Zahl. And this says, again, the same assumption, T is a set of delta tubes contained in the unit ball in R3, not R3, just Rn, n equals to 2 or 3. For any epsilon greater than 0, the following eta only small enough, only depending on epsilon, and delta also small enough, only depending on epsilon, the following holds. Okay, I should put this here. The following holds. Now T is it should read as this line about quantifiers, and then T is a set of delta tubes containing unit ball. If the Katz-Tau constant of tubes, delta tubes, is less than delta to the minus eta, then for any shading y of density greater or equal than delta to the eta, any y, so for any shading y with lambda y greater or equal than delta to the eta, we have the union is greater or equal than delta to the epsilon. So this is precisely our heuristic from the enemy example. And if the Frostman constant in B1 is less than delta to the minus eta, then for any shading with density greater or equal than delta eta, they are essentially disjoint, and this is essentially fill out the unit ball. Okay, so that is the main theorem we are going to talk about, and then now let's try to digest this definition, and so the first remark is that so if T satisfies the Kakeya assumption, then both the Katz-Tau constant and the Frostman constant is less than 1, less than some constant times absolute constant, depending on the dimension. So how do we see it? I think we basically said here, in this when we study this enemy example, for any delta, for any A times B times 1 rectangular box, the number of directions, the number of delta separated directions that could be contained in W is at most the volume of W times divided by the volume of T. So this, from that calculation, this says that this number is less than the volume of W divided by the volume of T. And now we just plug in the definition, for example, then what is, this is always less or equal than 1, because it's just this times the volume of T divided by the volume of W. So for any for any convex set W. So by Jones ellipsoid theorem, any convex set is like roughly up to roughly an A times B times 1 box after doubling. And also, we just said that, I erased this, a set of tubes satisfying the Kakeya assumption implies that the number of tubes is roughly delta to the minus n minus 1. And this implies that the density of T, since it's contained in B, if a set of tubes contained in B1, since it's contained in B1, it shows that the density is roughly 1. So this says that the Frossman constant, the Frossman constant in the unit ball. So usually when the W is unit ball, sometimes I omit this from the notation. And so this says that the density is roughly 1, and this implies that the Frossman constant in B1 is less than 1. Okay. So
these are two different estimates.
You mean these two?
It's a comma.
Yeah, comma.
Thank you.
Yeah.
It's not a product.
Yes. Yeah, that's true. And also, just another remark is that so previously when we studied the Kakeya set conjecture, it seems that the Kakeya assumption, which is 1 delta tube in each delta separate direction, is like the key definition. But from our definition notation, this is no longer essential, because the second thing is that, let's say, given theta to be 1 direction, and T is all like distinct parallel tubes, T, let's say, pointing in the direction of theta, then this also, T also satisfies the Kastel-Wolff axiom, and Frossman in B1. Or set of distinct tubes in direction theta contained in the unit ball. So it's like the same. You notice that this and this, they are satisfied the same thing. However, if we want to prove this theorem for this set of tubes, is like very easy, trivial. But if we want to prove this theorem for this set, it becomes very difficult. But this definition says that, okay, they should be treated the same way. Maybe let me just say, why do we use the words Kastel, Frossman, and also Wolff? So the reason is that Tom Wolff proved that any Kakeya set in R3 has dimension greater or equal than 5 halves. I think more generally, he proved dimension n plus 2 over 2, using an assumption that's quite similar to our Wolff axioms. Our definition, just my generalization of Wolff's original, his definition in this paper, he proves that if a set of tubes satisfies some Wolff axioms, which is like similar to what we have here, then it has the corresponding dimension, and this is much more general than the Kakeya set. So, and his proof also works not only in Rn but also works in Cn, and his proof, this result in R3 has been like a milestone result that's very difficult to improve, because after many years, all this result is like dimension. So Larry gives some characterization, but this result and this result shows like the dimension of the Kakeya set is greater or equal than 5 halves plus a very tiny number, and then this says like why Wolff's result is very significant, and one of his key insights is the Wolff axioms. So we are going to still use mild generalization of the Wolff axioms, but we are going to use crucially that here is containing Rn, where Wolf's result was, we'll see an example very soon that is in C, and that shows that Wolf's argument is sharp. And that is where the name Wolf comes from. And the Zahl and Frostman, this name comes from, we also see later, so usually when we want to discretize, let's say, a set of Hausdorff dimension S, there are usually two ways to discretize it. One way is, like, suppose we discretize at scale delta, and there is this Zahl delta S set, and also Frostman delta S set. They are like a discretization of S-dimensional set. Our definition is in the same spirit, but just for the set of convex set of delta tubes. So that's where the name Zahl and Frostman come from. Okay, so this is our sorry. Main. Is there water? Oh, I'm trying to get some water. Maybe let's take a 10 minutes break. So we'll continue talking about the proof in dimension 2. This is just using Cauchy-Schwarz, and this is due to Cordoba. So first we sum over the indicator function of shading for T contained in T. And then those functions has support on the union of tubes. Then this is just greater or equal than, because the shading has density greater than delta to the eta, so this is greater or equal than delta to the eta times the number of tubes times the volume of one tube. And then we take the square. And we take Cauchy-Schwarz. This is times sum over yt1 intersect yt2, t1, t2 in T. So in order to show that this has a lower bound, we just need to give an upper bound on the intersections. And this is, okay. I'm going to just use, like, the shading is trivially bounded by the T1 and T2 intersect. So this is less or equal than the volume of T1 intersect T2. And then fix T1 in T. We know that T1 intersect T2, sum over T2 in T is less than T plus sum over delta dyadic rho is the dyadic numbers between delta and 1. So there are log delta many terms. And the angle between T1 and T2 is roughly rho. So we know we just do a dyadic pigeonholing, and then how to give an upper bound on the right hand side. So if T1 intersect T2 is not empty, and the angle is roughly rho. So this implies the following. This implies that T1 intersect T2 to be less or equal than, okay. So the intersection has length. So because they have angle about rho, if they intersect, they stay intersect for length delta over rho. So this intersection has a volume delta over rho times delta to the m minus 1. And also we know that T2 is contained in the rho neighborhood of T1. Now, since T2 is contained in the rho neighborhood of T1, this is a good time to apply the Wolff axiom. So the number of those T2 is less than. So how do we apply the Wolff axioms? If the Castel constant is bounded, so it's less than delta to the minus eta times rho over rho to the n minus 1 over delta to the n minus 1 if Castel constant is bounded by delta to the minus eta. And this is bounded by rho to the n minus 1 times the total number of tubes if the Frossman constant is bounded. And now we can use that to plug in. So this is less than T plus, again, rho dyadic. Here, the volume is, I erase the word dyadic here, just rho. This volume is delta over rho times delta to the n minus 1. And then how many T2 are there such that the intersection is non-empty is this number. So times delta to the minus eta rho to the n minus 1 over delta to the n minus 1, or rho to the n minus 1 times the number of tubes if this is basically the argument. So let's just finish the algebra. Since there are dyadic many terms, so this term, we have rho here. So this term is less than the volume of T plus delta to the minus eta. It maximizes by the largest term, by the largest rho, because the exponent of rho is positive. And we have delta times rho to the, so no rho anymore, delta if Castel constant is bounded. And this is delta to the n times the number of tubes if the Frossman constant is bounded. Right.
So rho disappears in the first case because n equals 2?
No. Oh, sorry. Because n is greater or equal than 2. It does not disappear.
Greater or equals?
Yeah, so there is also a
rho to the n minus 2.
Yeah, so there is also a term that's like log delta here, but it's observed in anyway, so yeah, so remember it's n greater or equal than 2. So for now, all the argument works for any n, but here is when we see that when n equals to 2, then this gives exactly what we want. But when n is greater than 2, this bound does not give the optimal bound. Yeah, we can just continue plugging in. So, sorry, this becomes a little messy. I'm going to write this shorter. So this is less than times, we just need to multiply this term by the number of tubes. And this is always smaller, so because this is delta to the n, so times delta if Katz tau, delta to the n times t if Frostman. So we comparing this term with this term. There is the square here. And yeah, so you can see that this works nicely when n is 2, but not so nice when n is greater than 2. Okay. This is a good place to give exercise. So I'm going to call it claim, but the proof really uses just this L2 method and also the definition of those Wolf axioms. So claim 1 is, let's say T is a delta tube, and let's say Y0 T is a shading, and then we know the following: for any delta ball Q contained in the shading. So here I'm thinking about since the shading is a union of delta balls, so I'm just for any means that like YT is just a set of, we can think YT as a set of disjoint delta balls, and this means that for each of them, this is let T sub Q be a delta tube through Q, and the angle between TQ and T is roughly 1. So the picture is that here we have our T, and then we have a set of shadings, which is like a set of roughly disjoint delta balls. And then for each of those delta balls, there is another tube. This is Q. Another tube that intersect this transversely. The angle is roughly 1. Then the set T is the Q in YT has the Katz tau constant bounded by 1. So this is just by definition, like by going through the definition of Katz tau Wolf axioms. So this reason is also quite simple. Is that so for any box, because so those box also has to intersect T transversely because it should contain one of those yellow tubes. Since it intersects transversely, how many of yellow tubes can it be contained in this box? We know that for each point, for each delta ball, there is only one passing through it. So the number of the yellow tubes contained in this red box cannot be more than the number of those delta balls contained in this segment intersecting the red tube, because their angle is roughly 1, so the length of the segment is roughly the width of the rectangular box. And that is how we show the Katz tau Wolf constant is bounded by 1. So this is the first claim. And the second is more involved, and it uses as a corollary. So let's say YT has dense shading, then this implies that the union of those tubes is greater than So this is quite useful in later proof, for example, in the second part of the claim. Okay. And then the second part is, since we said that this proof in dimension 2 works well for the delta rectangles in dimension 2, so one analog of this proof is like delta times 1 times 1 times 1 slabs in higher dimensions. So that's the second part. Suppose S is delta times 1 times 1 slab. You could think it as like rectangular. So this delta 1 1 and y0 sub S is a shading. Again, this shading just means some union of those delta balls. But here I want the shading to be dense. Let's say y0s is greater or equal than delta to eta s. So I want this. I should draw a lot of them, but I don't have time. And we have the similar assumption for any delta ball Q contained in Y0S. There exists S sub Q is a delta slab such that the angle of SQ and S is roughly 1. So what this means is that, for example, through this Q, we have some slab that this is SQ, intersect S transversely. So this angle is like 1. So this holds for any of those delta ball in the shading. Then the conclusion is that so this collection of S is also going to be the collection of all those yellow slabs. But you might wonder what kind of Wolf axioms does this S satisfy? Unfortunately, I cannot really tell you. But what we know is the following. Or unfortunately, I don't know. But we do know something. We know that for any shading, dense shading, the union of those slabs is greater or equal than delta to the some constant times eta. So this is what we know. And this is again going to be used many times. The proof is also L2, so the same proof, but it uses this proof and also the part 1 of the claim. So the way we do it is to split into 2 parts. I'm going to just sketch the idea. So the first part is if a set satisfies the Kastel-Wolf axiom, then the union of those shading is roughly greater than, I'm going to ignore the epsilons, number of S times the volume of 1S. So this is one thing. And the second thing is, so this part uses just that proof, the L2 argument. And the second part uses some of the ideas in the claim, the claim 1. What it does is that we can choose a random line let's say this blue line, such that this blue line intersect a lot of those delta balls in the shading, and also such that this the corresponding slab with the delta balls intersect the blue line transversely, not blue, green, sorry, green line transversely, and the thing that it intersects the green line transversely, then we show that the set of those SQ from the delta balls in this green line will satisfy this Katz-Tau-Wolff axiom. Uses the same as the claim one, and so let's call this L, and we show that this Katz-Tau-Wolff axiom of SL is bounded by 1. So SL just means the set of those slabs corresponds to the set of SQ with Q on L. And also the SQ has to intersect this L transversely, and this uses this assumption. Such line exists by random choice. Okay, I'm omitting a lot of details, but I hope this, at least the idea is roughly clear. We are going to use those two claims in the later proof. And so this, I think this finishes on the story of the two-dimensional case. We present this L2 argument, and also we presented the two claims that will be used in three-dimensional case. Okay. Are there any questions?
So are the claims true in any dimension?
Yes. So, yes. Good. Yes. That the claims are true in any dimensions. But as you can imagine, the main thing we are going to use is this delta times 1 slab in R3. Are there any other questions? So, and what happens in dimension 3? So we said already the Wolff's bound, the dimension of the Kakeya set is greater or equal than n plus 2 over 2. Also his bound works for like delta tubes in any field, or lines in any field. So, and the reason why it is hard to improve this bound is because of the Heisenberg group. Example in C3, and this was discovered by Katz, Laba, and Tau. And it plays an essential role in our intuition about the enemy examples of the Kakeya set. And well, they show that the Minkowski dimension of any Kakeya set in R3 should be greater than 5/2 plus tiny epsilon. And to do the proof, they discovered this important Heisenberg group example. The one we present is slightly different than they originally have. So let's consider this. I'm going to call it H as Z1 square plus Z2 square minus Z3 square equals to 1. So they are in C3. So we first show that this H contains a lot of complex lines, because since we are considering C3, then the unit line segment should be complex line segments. So through how many complex lines, like how large is the set of complex lines? So through this point, P equals to 1, 0, 0, we know that this is a cone. So each of this is the complex lines, C lines, theta z, theta, let's say, so this is a complex line, and so this means that through, and that is a cone containing one real dimensional set of complex lines. So, yes. So because this cone is also contained in this H, and as we can see, those are the complex lines contained in H. So then this implies that, first of all, H has real dimension 5, because if we identify C3 with R6, then this is hypersurface in R6. So H has real dimension 5. And also H, how many complex lines does H contain? So since it has 5-dimensional set of points, and each point contains a one-dimensional set of complex lines, so this means this is the number of incidences. So the dimension of incidence is P contained in a complex line L. And each complex line contains 2 real dimensional set of points. So means that we overcount the complex line by 2 dimensions. So this gives us 4-dimensional set of complex lines. Since any Kakeya set in R3 contains a 2-dimensional set of lines, if we double the exponent by 2, so this is like 2 times 2 equals 4. So this means that the Heisenberg group looks very much like the Kakeya set in R3, except that it's contained in C3, and also this H, if you calculate, it also satisfies this convex Wolf axioms. So this is sharp because it equals to 5/2 times. And so this is where the Wolf's exponent coming from. And this is why it's very difficult to improve Wolf's bound for Kakeya sets in R3. So while in this very influential paper of Katz, Laba, and Tao, they discovered this example, and they also showed that any Kakeya set in R3 should have, if it has, so what they showed is if the Minkowski dimension of a Kakeya set equals to 5/2, then the Kakeya set is sticky, grainy, and plany. So in particular, this stickiness plays a very big role. As we discussed our plan, the plan is to first prove the sticky case of the Kakeya set conjecture in R3, and then prove the general case. So this, at least for the Kakeya set problem, the notion of stickiness comes from this paper. In fact, we discovered that the idea of sticky sets present in a much larger class of problems in projection theory, in geometric measure theory. I'm happy to talk about it after the the class. So this, I hope, gives us some motivation to study the sticky case, and I'm going to define what is sticky case in our setting. I should also say that the Heisenberg group is sticky. So that is also another reason why the sticky case is so important, because the main enemy is sticky, and is like, as long as, so our first step is in the sticky setting, we rule out this enemy using projection theory and a lot of structure. And then once this is ruled out, we use the sticky case as a base case for induction and prove for the general case. Okay, so I hope this concludes my hope was for the first hour, but then it's like 2 hours passed by. Okay. I think you can erase that. Okay, oh, actually 1.5 hours, so it's fine. So now let's talk about sticky case. I'm going to define it. Sticky Kakeya sets. So I think it should be more general. Maybe that's just, it's not really just Kakeya set, but more general notion. So our definition of stickiness is slightly more general than what Katz-Lapa and Tao define in their proof. And this is, roughly speaking, what it means is that a set of delta tubes is sticky if it satisfies those Wolf axioms at every scale. But I will define what is rigorously what it means. So let's first do some pigeonholing. So setup. So this is a very general setup. Let T be a set of delta tubes containing a unit ball. We can say, when we say that T is, again, T is a, so delta tubes, we say that T is uniform. Sometimes we even add a quantifier here, say that is delta to the eta uniform. But when eta is clear from the context, we sometimes just say that T is uniform. If the following, if for any rho equals to delta to the j eta, so j is integers from 1 to eta to the minus 1. So we can decompose T as the set of delta tubes contained in each rho tube. So this T bracket rho, is the set of delta tubes contained in a rho tube, and this blackboard T rho is the set of rho tubes. So it's like so those rho tubes are going to cover delta tubes. And this is we can decompose T as the union of the thin tubes inside the rho tube, such that for each T rho, such that this T, the number of delta tubes contained in rho tube is roughly the same as T rho varies in our collection, and this implies that the number of tubes is roughly the number of rho tube times the number of delta tubes contained in rho tube. This is so that's finished the definition of delta to the eta uniform, and by pigeonholing any set of delta tubes, there exists a delta to the eta uniform T prime, and T prime is a significant subset. So this is just a pigeonholing definition, and from now on we will always assume that the set of delta tubes that we're working on is uniform. Okay. This is helpful because then here comes the definition of stickiness. We say that let's say delta eta uniform.
Sorry, so you use the same notation? It's difficult for me to distinguish between T and T here. Is that there exists delta uniform T including
T prime.
Sorry.
Prime.
Prime. Ah, prime. Thank you. I haven't seen this prime.
Okay, so we say that delta to eta uniform set of set of delta tubes T is sticky let me just also use the notation delta to eta sticky. So what this really means is that it satisfies the Kastel-Wolff axiom at all scales if for any rho equals to delta to the j eta and all the j's here, we have the maximal density of T rho, where T rho is defined as such, is less than delta to the minus eta. This is the same thing as the Kastel constant of T rho is less than. Okay, so that is the definition of sticky sets. The difference between so sometimes this is just shorter, but sometimes what I prefer to write is T satisfies Kastel-Wolff axioms at all scales. That sometimes I prefer to say that, but writing delta to the eta sticky is just shorter. But what this definition really means is follows. The difference between a set of tubes satisfying Kastel-Wolff axiom and sticky sets is just whether it's at all scales, means for all rho or just for T. And the theorem we prove is follows. I should say that this theorem was inspired by, based on ideas of Katz and Tao. That Tao outlined the idea in his blog post, and we were inspired by this blog post. So it's the same quantifier. Let me just rewrite it. For any epsilon greater than 0, any eta and delta, the following holds. If T is a set of delta tubes contained in a unit ball, is delta to the eta sticky, then for any delta to the eta, for any shading y on T with density greater than delta to the eta, we have the union of tubes has volume greater than delta to the epsilon. So this is our sticky Kakeya theorem. Okay, so that is the second topic. So we are hopefully going to outline some of the ideas in the proof. First of all, again, let's digest this notation, why this is useful. So if a set of delta tubes is sticky, I'm going to ignore this quantifier a little bit. Then this implies the following. So it implies T rho is sticky. You might ask, what's sticky? So this is miniform when, let's say, rho is less or equal than delta to the some epsilon. We call this epsilon scale. It's now here comes a lot of epsilons. So this just means that when rho is, you should think this epsilon as very small, but this is miniform when rho is like away from delta and also away from 1. And then this T rho is sticky. You can calculate what is sticky, but what should I replace with delta to the eta here? The thing is that when epsilon scale is much larger than eta, this is still a miniform sticky notation. And also we know that T bracket T rho is sticky. Again, this makes a lot of sense when rho is not too close to the endpoints. So this notation means that the sticky set of delta tubes is particularly good for induction because it's still sticky, maybe to a less extent after thickening, and also it's still sticky after restricting to a thick tube, after taking all the thin tubes inside a thick tube. So this notion overcomes the issue we talk about when we study the set of delta tubes satisfies the Kakeya assumption. Then this Kakeya assumption does not preserve under thickening or restricting to a small box. But this notation, this definition, is good to do induction scales, and we are going to explore this a lot in the study of the sticky Kakeya sets. Maybe I should pause. Are there any questions?
I'm sorry, at the end, the proof of the sticky case will be used to prove the general case?
Yes, in fact, that's a very good question. So the plan is that some of the ideas, the first part of the ideas will still be used later, that I'm going to talk in details, a lot of details. But the second part of the idea is specialized to the sticky case. I'm going to just sketch the outline the idea. The sticky Kakeya theorem, we are going to use it as a black box to prove the general case. But even though the black box, the first part is pretty general, and some of the technique will be used later.
Black box.
Yeah. So yes, I should say that the picture gets quite involved for the sticky case, especially for the second half. But it's going to be black boxed. That's why I'm only going to just draw some pictures and try to tell you how it's related to other problems. Okay. Yeah. And this, I think, I don't know whether I should write this here or, but it's, okay. Yeah, so I will be very clear which part is going to be black box and which part is going to be used later. Okay, so I'm going to do the first claim. It suffices to prove theorem 1 with the additional assumption that the set of tubes is roughly delta to the minus 2 in R3, because it's going to be important that this is in R3. It's still unknown in higher dimensions. So on this claim, I'm also just going to sketch the idea how to do it. It's just some randomizing argument and like manipulation of those Kastel constant. So the first statement is follows. It's a consequence of the definition of the Kastel-Wolff axioms that I hope is still there. Is less. So usually I'm using this notation to hide like subpolynomial powers of delta. For example, delta to the, let's say, minus eta for some very small eta, or even like log delta to some power. Okay. Yes. So this tells you that again, we assume that the set of tubes, they are uniform. So everything is uniform. So those are all well defined. Well, if you really want this to be well defined, I should also take a sup. Let's say sup of T rho J minus 1. But in the actual proof, we are going to do pigeonholing so many times that everything here will just be the same. So, but we have that. This first part is, well, it's not too hard to prove because it suffices to prove, let's say, we have two scales. So the proof idea for the first part is just let's say we have one row delta max of T row times delta max of, so times the sup of T row. So how to do this? Well, we have those row tubes, and we have a collection of delta tubes. and we probably have some other rows here. And we want to estimate the density. We just decompose if we have a rectangular box W, and then we decompose. Let's say A, B, 1. So we decompose into whether A and B are larger than rho or not, and then study case by case. So I'm happy to answer this during the break. It should be a very simple proof, just digesting the definition of how convex sets intersect tube. So once you prove this for one row, and then it's automatic that this holds for a sequence of rows for the uniform sets. And so this is the first part, that this tells us something about the density. And the second part is that the following randomizing argument that I'm sure the audience is much better in probability than I'm, so I trust you can do it. If the maximum density of T is less than delta to the minus eta, then there exists delta to the minus 2. I'm specializing in three-dimensional case, but this part is very general. It holds in any dimensions. This many rigid motions Rj, maybe I shouldn't use J, Rk, such that if we take T0 to be the union of Rk T, then T0 has cardinality roughly delta to the minus 2, and the density, maximal density of T0 is less than delta to the minus eta. So when I say roughly, it's all like up to polynomials of log. And this is because when we consider those maximal density, we are taking max over all set of rectangular boxes, but in reality, the collection of rectangular boxes we are considering is only polynomials of delta to the minus 1, because we are taking the essentially disjoint collection of rectangular boxes. So like the constraint here, those when we max over W is only polynomial powers of delta, but when we take those random rigid motions, there is this exponential that dominates. So this holds. This is random. Maybe I should say that if we choose this many random rigid motions with high probability, this holds. Okay. And how are we going to use this two statement to prove this claim? Well, we take this many rigid motions and then yes, and so this is, we first do step. Okay, so what we are going to do is, this works for only one scale, but to satisfy this stickiness assumption, we need to show the corresponding delta max T rho for all scales. So we are going to first, let's say, take this to be rho j minus 1, let j equals to eta to the minus 1. These are delta tubes. We first apply the second statement for the delta tubes inside of T rho, and then to make it such that the cardinality is full, it's like 2 dimensions. And then the second step is we are going to study the set of T rows in a larger, the set of T row J minus 1 in row J minus 2. And then we're going to again use the second claim, this randomizing argument, such that, so the first step is to make sure that this max of, maybe I shouldn't use T naught, let me use T star. Then it's going to be clear that when we take star, something is happening. T star T row J minus 1 is less than, and then the corresponding, this cardinality is 2 dimensions. And similarly, after this step, we're going to make the delta max of T row J minus 1 star in T row J minus 2 to be less than delta to the eta, and also have the similar cardinality. So you might think that we have many etas multiplying together. So the trick is that, okay, we could take, let's say, we are not considering, previously we decompose our scales into eta spacing. But here to do so, we could take a larger spacing, and then we don't multiply that many etas, so this is still true. I hope that explains how to reduce the proof of theorem 1 to this special case that the number of tubes is roughly delta to the minus 2. It's just some randomizing argument. I know that this part I'm going a bit too fast, but are there any questions? Okay. Okay, I'm going to just, before the end of today, I'm just going to talk about some refinements and also discuss the definition of multiplicity. Those things are going to be used in the non-sticky case, in the general case as well. So I'm going to go through them very slowly. This part is, I went through it very quickly because I think this is self-contained and is basically digesting the definition and then use this probabilistic argument. It's more disjoint for the rest of the argument. That's why I went through it quickly. Okay. Maybe I should write it here. But what I'm going to talk about for the remaining maybe 20 minutes or something will be used later, so we should go through it carefully. So we say that y prime is, let's say, lambda refinement of y. So the first definition is quite simple. If for any tube in our collection T on y prime, this is a prime, T is a subset of yt. It's also a shading, and then the density is still sufficiently large. So this usually, so I think in almost all cases, lambda is greater, approximate than 1. Or delta to the eta. And I should say that throughout the entire argument, we are going to use refinements so many times that sometimes I will just say without defining new notations. So this is going to be used over and over. And so here is another definition is about multiplicity. Mu T Y. It's roughly speaking, it is the number of tubes through a typical point. But what I'm going to do next is to say that after refinement, this is true, not just heuristic. So the multiplicity is defined as sum over the shading divided by volume. So in other words, to prove this theorem is equivalent as saying the multiplicity is less than delta to the minus epsilon. So up to some etas. Okay. Another definition is that let's say X be a delta ball. We say that T sub Yx is just the collection of tubes such that X is contained in the shading of T. So heuristically, this cardinality should be roughly the multiplicity, and this is true after refinement. Okay. So here is multiplicity and refinement. Okay. What are we going to do is define y prime t as the set of x in yt such that is roughly mu. So mu is a dyadic number. There exists mu such that if we define y prime t as this, then y prime is a refinement, like log 1 over log delta refinement of y. And we have the follows. We have this very simple, but I think a very convenient observation. The multiplicity of t with respect to the original shading is less approximate than the multiplicity of t with the new shading, and which is the same as t y prime x for any x contained in the union of t y prime. Yeah. This is just by pigeonholing, and it's very convenient. Let me just say why the first one is true, even though for some of you this might be very simple. We write out the definition. this is defined as sum of yt and this is defined as sum of y prime t. So I guess for the first inequality, you might ask, why the multiplicity in some sense increases after refinement? Heuristically, it should be decreased. But the point is that it is a very significant refinement. It's like roughly one refinement. And then we have the following. This is less than some log delta times this term. So it's true. This is because it's refinement, one refinement. And then second part is just trivially because this is a refinement. The volume is greater or equal than the volume of y prime. And since this is here, that's why we have less or equal. This is a quite easy argument, but just that it helps us to think through refinements. Like we feel much safer to take refinements because no matter how many refinements we are going to take, as long as it's bounded many times and each time is roughly one, then it suffices to bound this term instead of this term. And our main goal is to bound the multiplicity. So that's why throughout the argument, sometimes I was just replacing y by refinements without even saying it because it's okay, we just bound this term. And the previous term will be bounded anyway. And also, like for these refinements, I forgot to say that this part holds in a much larger generality. It's like this is true for any one refinement, regardless how we refine it. But what this part is doing is tells us that after some nice refinement, the multiplicity is really the number of tubes through a point. We are going to do another pigeonholing. I'm going to erase this. That helps us to visualize the multiplicity. Okay, this is more pigeonholing. We may assume that for any row of the form delta to the j eta, and for any t row in collection blackboard T, so previously we just assumed that this multiplicity is roughly the same, but now I'm going to say that in an even more refined way they are essentially the same. I should move this here. For any x in union of t row and t row in. So what this is saying that is that after a lot of still like one refinement, we can assume everything is quite uniform. So what this notation means, it means the following. Let's say this is rho, and let's say this is x. It just says that for any row, the number of thin tubes whose shading contains x is roughly the same as we vary our x and as we vary the t row. And this holds for this many rows. So and now this is very convenient because what we are going to do next is that we're going to study the following. So the thin tubes inside the thick tube will intersect into these segments that we discussed previously, because then the segment has length delta over rho, right? And if we call those segments G, the grains, which has dimensions delta times delta over rho, then we have the follows. And we can also define, let's say, G. G is the collection of those grains. And we can define Y, G, as just, let's say, the union of YT intersecting G for those T that contains G. Basically, it says that we take the shading of all those tubes passing through it. And then this gives us shading. And what this part is saying is that mu T Y, if everything is uniform in this sense, is roughly the same as mu T bracket T row Y times mu G Y. And this is all well defined because each G you represent roughly the same number of thin tubes containing it. Let's say less than. Okay. And this decomposition, we are going to see it again and again. But that is by going through shading and going through pigeonholing and refinements. I think this is the rigorous setup. We are going to see it in the sticky Kakeya proof. We're also going to see it in the general proof, just this simple decomposition, and how to make sense of it is via this pigeonholing and refinement. Yeah, so before the end, let me just talk about inductive statement to prove this theorem one. So previously we said that this is equivalent to the multiplicity bounded by delta to the minus epsilon. So we say that the statement, let's say K sticky beta, to mean the following. Again, this, okay, so for any epsilon greater than 0, any eta between 0, and now I need to add a beta here. The following holds for any delta between 0 and delta beta epsilon. Suppose T is delta to the eta sticky, and the number of tubes is roughly delta to the minus 2. And Y is delta to the eta dense shading on T, then the multiplicity is bounded by delta to the minus beta, minus epsilon. So I know that you might think, why do I need both beta and epsilon here? It's just to make this statement cleaner. We are going to do a self-improving argument. So we are going to prove that this sticky beta implies that for some new positive, if beta is positive. So this, I think, k as 2 holds trivially. And so this is a self-improving argument. And then the reason why we set up with both beta and epsilon is that it's just some abstract arguments. They're saying that the set of beta such that k as beta holds is a closed set. So we don't have to keep track of how small nu is. That's it. Yeah. And that's why we have this two parameters. So yeah, I think I will stop here, and starting from next time I'm going to talk about the argument.
Thank you. Time for questions. Yes.
Yes, there's a question. I'm not sure whether it's meaningful for them here. The European Kakeya conjecture started a straight line, and is it meaningful if you replace a straight line as a kind of a curved object?
Yeah.
Like, is it useful? Like, so I'm curious. For example, maybe to the curve the Kakeya maximal function.
Yeah, it's a very meaningful question because for the wave packets coming from the Hammond operators, they are naturally curved. So it's a very meaningful question to study.
So in this you feel that for curved Kakeya conjecture, will it be like more difficult, or like so? How do you feel about its difficulty and the distance from the current methodology?
So first of all, one needs to give the correct definition, because for some notion of the curved Kakeya conjecture was disproved by Jean Bourgain. He said that for generic Hammond operator, the corresponding curved Kakeya conjecture is false. Then there's one thing, and then how you define it. Maybe this method could have some hope of studying that, but it also depends on how you define it.
Thank you.
Some other questions? So the last part of the argument, I see, so you start by 2. So what is not going to work in dimension 4, let's say?
So far, I haven't explained what's not going to work, but it is going to be, okay. It's going to be clear later.
First of all, do you think is it true, the conjecture is true in dimension 4 or not?
I think the sticky case should be.
Sticky case is true.
General, I'm not sure yet.
Then you have to, okay, we have to see how far the sticky compared to the general.
Yeah. So we have to see a lot of arguments, and then I could point it to you, like which part it has more difficulty in dimension 4.
Okay.
Yeah.
Okay.
But so far, you don't see it yet.
Okay. Good. Thank you. Yes.
Maybe a silly question. So at the beginning, you made a remark about you could maybe just to get a sense of the argument that you could let the shading just be everything.
Yeah. Then those steps. Then those are not rigorous anymore, but just holds heuristically.
Okay. And the question is, if you just look at the statement without the shading stuff, is that a meaningful question? Does that say something interesting? Does the proof simplify significantly? No.
So first of all, we need the version with shading to recover the Hausdorff dimension version, and also, as you can see, the proof involves a lot of refinement, so the shading will come naturally. Okay.
Yes, please.
Yes, so thank you very much. I was wondering, now that the conjecture is solved, what would you say is the understanding we gained from a general point of view?
I think we sort of understand how to estimate the union of tubes in R3.
It's very good that all these computations are done, but to a non-expert, what is the big picture view that we gained on the conjecture?
I mean, previously we don't really know how to study union of tubes. Even in dimension 2. Now we understand dimension 2 and 3 pretty well. 3 somewhat well and 2 pretty well.
Okay.
And then, maybe to really answer your question, I've been focusing on tubes for so many years that I forgot there are other problems in life. But then I think the motivation why we care about union of tubes is that so the tubes are the support of something called wave packets from for example, Schrödinger waves, and so it gives us a better understanding of how wave propagate. And also, probably I should give a motivation why Kakeya talk, like why this conjecture is useful. So the Kakeya set conjecture and also like trying to understand union of tubes problem. So there are a sequence of conjectures in harmonic analysis that would imply the Kakeya set conjecture, meaning that it lies in the we need this to be true for a sequence of it to be true. Also, there is a conjecture, difficult conjecture in number theory called Montgomery's conjecture on large values of Dirichlet theories. It also implies the Kakeya conjecture, so we really hope it's true.
So, but you want to see these tubes fundamentally as support of some solutions, or?
Yeah, it's yes. So you can partition your wave functions, decompose your wave functions into wave packets, and each wave packet supports on one of those tubes.
Okay, good. Thank you.
Thank you. Some more question? Yes.
I have a silly technical one. So in Cordoba's argument, well, you use holder and you end up with intersection of 2 tubes.
Yeah.
I suppose that if you start from the cube, you can end up with intersection of 3 tubes.
Yeah.
And of course, you're not going to end up with the Kakeya conjecture, otherwise it would have been solved 40 years ago. But what do you get in 3D when you do the L3 bound in that way?
That's a very good question. So first of all, when you say L3 bound, then already in R3, a typical intersection is empty, and it's more empty if we intersect with another one.
Yeah, sure. I mean, you would have to sum over the points where.
The difficulty is that you don't know when it's empty or when it's not. So you only use the worst possible scenario, and so this is a very bad bound, even with this in R3. I think that's one of the main issue in R3 is that for a lot of the intersections, a typical intersection should be empty, but you don't know when it's empty. So you can only use those trivial bound, the worst case, and this is very bad. It's even worse with 3.
Very good. And we are on time. So perfect.
Thank you.